Hi, and welcome back to part 2 of Mr. Collins's Introduction to Chemistry unit. This is video 2, part B of Stoichiometry in the mole. And we had some technical difficulties with part A, but it was actually a good place to stop because we just finished talking about the theory behind the mole, and now we're going to apply it to some more complex chemical situations. That involves the use of stoichiometry. Now, stoichiometry comes from the word stoichion, which means element, and metric, which means to measure. So to put that together, we're measuring elements. And I think the picture on the screen is a good look at how some students feel about stoichiometry. It can be a little daunting, but it doesn't have to be. And I want to show you why. Let's make a peanut butter sandwich, something as simple as that. Now, I've got my iPad here, and I'm going to be drawing some notes on that because I want to show you how I like to organize my thoughts when I try to attempt a chemical question. So first thing I like to do is summarize. So we're making a sandwich. Which weighs more? 1 serve of peanut butter, 1 slice of bread. So let's write down the information. You can see at the top there, 16 grams equals my peanut butter, and 40 grams equals my bread. Okay. So of course, the peanut butter weighs less than the bread. The bread is 24 grams more than the peanut butter. So in one sandwich, next question, 1 slice of bread, 1 serve of peanut butter. That's how we're defining a sandwich. Not 2 serves, maybe fold the bread in half or something like that. What percentage weight is the peanut butter? Now the reason I've included this is because it's really important, and it's assumed in Year 11 chemistry, that you know how to use percentages. The word percent means out of 100, cent meaning century. So we convert whatever we have into a scale of 1 to 100, where the full number is 100, and I guess 100th of that is 1%, and obviously anywhere in between or even lower than that. So when we're looking at this question, we need to first work out what is the whole, because a basic way of looking at a percentage is you take the number in question and then you divide that by the whole multiplied by 100. Let's do the example of peanut butter. So peanut butter in question multiplied by the whole. What is the whole? Well, 16 plus 40 equals 56. So one sandwich is 56 grams, so 56 multiplied by 100, and that is going to equal, let's do that calculation again, 16 divided by 56 multiplied by 100, that equals 28.57%. So that's the percentage of the peanut butter. Let's have a look at the percentage of the bread. It's the same thing again. This time though, we're not interested in the peanut butter, we're interested in the bread, which is 40 grams divided by the totals, which is 56 multiplied by 100. So let's do that, 40 divided by 56 multiplied by 100, it equals 71.428%. Okay, if I have 40 grams of bread and 40 grams of peanut butter and I combine them to form a sandwich with only 1 serve of peanut butter, not 2, how many grams of sandwiches will I make? Well, you might think that because I've got 40 grams of bread and I've got 40 grams of peanut butter, well, that's going to equal an 80-gram sandwich. But of course, we don't need to use all of our peanut butter. We've got more than we need. A chemical way of saying that is we are making a sandwich in excess peanut butter. And our limiting reactant is bread. Our limiting reagent is bread. Once we use up all the bread, that's it. No more sandwiches. In fact, we're only going to be able to make 1 sandwich. How much is a sandwich again? Well, we're going to be able to use all of our bread, but we're only going to need to use 16 grams of that peanut butter. So again, since we're only going to be able to make 1 sandwich, that's 56 grams. So how many grams of sandwiches will I make? Well, that's 56 grams. How much peanut butter will be left over? Well, 40 grams is what we have. We only need 16, and so that's going to equal 24 grams. We're going to have 24 grams of peanut butter left over, which is 1.5 servings. If I have 8 grams of peanut butter, how many grams of bread do I need to fully use up the peanut butter? This is interesting. We're not going to be able to make a full sandwich here. If I have a look at that 8 grams and I divide that by how many total grams it is, that's going to equal 0.5. I've only got half a serving of peanut butter, and so therefore I'm only going to be able to make half should be there, a serve, oops, let's go back, half a serve of half a slice of bread, sorry, and that's 20 grams. Okay. The reason I've been talking about sandwiches is because this is exactly what you would do with elements, except replace the peanut butter with oxygen, replace the bread with calcium. In 1 mole of calcium oxide, what percentage weight is the calcium? What is the oxygen? Actually, let's go back. How much does 1 mole of calcium weigh? Let's go to our periodic table. 40. Let's round that down to 40. And what about the oxygen? 16. So you can see the reason I chose those figures is because it's to react calcium with oxygen is very similar to making a peanut butter sandwich. And I won't go through all of these answers. You can work those out for yourself because it's actually exactly the same as what we did before. The same underlying mathematical concepts. Now, let me explain why we need to use the mole. Because chemists work with measurable units when doing experiments. So if I'm weighing something, I'm going to be weighing it in terms of grams. I'm going to be measuring the concentration, we call that molarity. Or maybe I'll be able to measure its volume in terms of liters. But chemical equations deal with moles. I'll go back to this slide in a moment, but when we look at a chemical reaction, I can look at it in a few ways. So iron and oxygen, iron 3 oxide, there's the symbols. I can look at it in terms of 4 iron atoms react with 3 molecules of oxygen to give 2 formula units, it's the term there, of iron 3 oxide, sorry. Or I can look at it in terms of moles. So I could say, let's scale this up by a factor of 6.02 times 10 to the 23rd. I can say 4 entire moles of iron reacts with 3 entire moles of oxygen to give 2 entire moles of iron 3 oxide. And this scale is something that we deal with most of the time. Now this is the balanced reaction here. 223 grams plus 96 grams gives 319 grams. But what if I have only 100 grams of iron? How many grams of iron oxide am I going to make? It's actually a little complicated. So what chemists do is they go from the grams they have back to moles, then do a mole-to-mole conversion, sometimes called a mole ratio, and then get the answer back into a measurable quantity again, such as grams, and that's what they do for their answer. Let me explain a little bit more, and we'll do a few examples in a moment. So, as I said, you can read this here. If you have a measurable substance, example 10 grams of calcium carbonate, and you need to calculate the mass of CO2 produced by this reaction here, you must first convert your known substance to moles. Because the numbers here, these aren't grams. This isn't 1 gram reacts with 2 grams to give 1 gram, 1 gram, and 1 gram. It's 1 mole reacts with 2 moles to give 1 mole, 1 mole, 1 mole. And obviously these mole amount, because they're different elements with different molar masses, are different. So we can't use grams. We have to go through moles. And I like to say this. I like to say that all roads go through moles. So when in chemistry you measure something, you'll either measure its concentration, volume, or mass. You'll convert that to mole, then of the product you want. You'll do a mole ratio. For example, if I'm in the question I was looking at before, you can see that calcium carbonate to carbon dioxide is 1 mole of calcium carbonate in this balanced reaction gives 1 mole of calcium carbon dioxide. 2 moles of hydrochloric acid give 1 mole. That's the ratio. So the first ratio was 1:1. The second ratio was 2:1. So we need to consider that ratio, which I'll go through in a moment. Once we've done that, we know the second, we've done the ratios, we've got the moles, then we convert back to our measurable quantity. Stick with me, because before we talk about mole ratios, I need you to actually understand the maths behind ratios. So let's take 5 orange, what do you kind of call those, discs and 4 blue discs. We can say that we have a ratio of 5 orange is to every 4 blue. That's the same ratio as 2.5 if I halve everything. 2.5 is to 2. Or I can double it, 10 is to 8. Triple it, 15 is to 12. I can multiply it by 7, 35 is to 28. It's the same ratio. Now ratios can also be written as fractions. If I take 5 and I divide it by 4, that equals 1.25. If I take 10, the same ratio just multiplied by 2, and I divide that by 8, I'm going to get that same number. I'm going to get, in this case, 1.25. And so this knowledge of ratios, that they can be divided, and even if you multiply them or divide them by a common factor, that the fact that they're always going to give that same ratio number, in this case 1.25, for 5 is to 4, 5 divided by 4 is 1.25, then we can use that to determine things. Now, a lot of you will be able to do these kinds of things in your head for easier questions, but I'm going to do a little bit of a harder question. Now, what I'm going to do on my iPad here is not the full working out, otherwise that would take too long. I will do a question with full working out at the end, but again, the iPad's just there for me to jot down some thoughts. The full working out I've actually pre-prepared on the slide. So let's have a look at this question. And it's not the easiest question to understand from its wording, and I think that's a good thing, because part of chemistry is actually working out what exactly do I need to know. So I have 2.6 moles of N2, so let's write that down, 2.6 moles of nitrogen gas. How many moles of H2 are required, and write question mark mole of H2 are required to make NH3. NH3. Okay. With no nitrogen left over. So that means it's a minimum amount of hydrogen that I need to react completely with nitrogen. What's this question actually asking? The first thing I would do is I would write down an equation. So let's have a look at that. Nitrogen plus hydrogen is going to give us ammonia gas. That's not balanced, is it? Let's try to balance that. Let's start with the big one first. Clearly our nitrogens aren't balanced. Remember, I can only change the coefficient. I can't change the subscript. Can't change the subscript, can only change the coefficient. So now I've got 2 there. That balances with the nitrogens. What about the hydrogens? Well, I've got 6 on the product side. I'm going to need 6 on the reactant side. I can do that like this. So there's the balanced equation there. Now I can see my mole ratios. 1 nitrogen reacts with 3, so 1 is to 3 hydrogens to give 2 ammonia molecules, NH3. So 1 is to 3, 1 is to 2, or in this case it's 3 is to 2, depending on what you're asking. Okay, so if this question was I have 1 mole of nitrogen gas, how many moles of hydrogen gas are required to make NH3? Well, I could easily, if the question was, this wasn't 2.6, if this was just 1 mole, well, clearly from my balanced reaction, I would need 3 moles of hydrogen gas, because that's the ratio, it's a 1 is to 3. So hydrogen is always 3 times more. So there's a quick and easy way to do this. You can probably do this in your head, to be honest. You can go 3 times 2.6, 3 times 2.6. Gives us 7.8. And this will get you by for now. So obviously the answer to the question is 7.8 moles, the mole ratio. But I want to teach you to do it a way that's foolproof, so even if the numbers are really obscure and it's really hard to work out, you'll still be able to do it. So what you do is, I know that the ratio in question is the ratio between nitrogen and hydrogen, 1 is to 3. The new ratio is 2.6 is to X. What's X? Well, we just worked that out in our heads as 7.8. But let me show you what you actually do. So 1 is to 3 is equal to 2.6 is to X. Well, remember, these can be converted into fractions. So 1 divided by 3 is the same. Actually, I'll do it like this. I'll do 1 divided by 3 is equal to 2.6 divided by X. And when I write it as a fraction, I can now cross multiply. So that gives me 1x, or just x, equals 3 multiplied by 2.6. So that's actually what you did in your head before. And that obviously equals 7.8 grams. Not grams, moles. M-O-L. So the written answer is 7.8 moles of H2 are needed to react with 2.6 moles of N2. Let's do another question now. I'd like you to try this question by yourself. I'm not going to go through this on the iPad, but I'd like you to give it a go. I've put the balanced equation up as before. We already had that. This question is, I have 2.6 mole, that should be moles in plural, of nitrogen gas. How many moles of NH3 will I make if I've got excess H2? So if I've got more than enough H2. Well, again, if I had 1 mole of nitrogen gas, well, based on this reaction, of course, I would be making 2 moles of NH3, ammonia gas. Let's see if you can work it out. Now, the easy way is just multiplying 2.6 by 2. But the foolproof way is to do it through understanding what a ratio actually is. So I should say, if you want to pause the video and work it out, now's a good time to do so, but I'm going to go through the answer now. So molar ratio is 1:2. The new ratio is 2.6 is to x. You write that as a fraction, you cross multiply. So 1 multiplied by x, 2 multiplied by 2.6, and you get 5.2 is the final ratio there. So 5.2 moles of NH3 can be made with 2.6 moles of N2. And it's important to write out your answers in full, especially for exam situations. So if you would like to do these mole ratio conversions or mole to mole conversions, I'll link in the video description a few resources for you to do that. Now what we're going to do is something a little more complicated. So we're going to convert our answer in moles to mass, but I'll change up the question a little bit. So let's say instead of what we had before, what was that, 2.6 moles? Let's say you have 2.5 moles. How many grams of H2 are required to make NH3 with no N2 left over? Well, I need to first work out how many moles of how many moles of H2 I'll be making. And then once I know that, I can convert moles into grams by using the mole to gram formula. So we start the same way we did before. We do a mole to mole conversion. So we write down the balanced equation, we write down the molar ratio, and we work out that 2.5 moles of nitrogen gas need 7.5 moles of hydrogen gas to completely react. And so let me write that down. So 7.5 mole of H2 needed to completely react with N2. How much N2 was it? It was 2.5 moles of N2. Okay. So I can't leave my answer there because it actually asked for my answer in mass. So how much is 7.5 moles of H2 in grams? 7.5 mole of H2 equals question mark grams. Well, of course I can use my mole to mass formula. Moles equals mass over molar mass. So my moles we know is 7.5 moles. My mass, well, I'm going to leave that as M because I don't know it. And my molar mass, let's go to the periodic table. Hydrogen is 1, so it's going to be 1 plus 1. Remember, it's H2, so we've got 2 individual hydrogen atoms. And when I do some algebra, so 7.5 multiplied by 1 plus 1 is 2. Chemistry involves some pretty simple maths from time to time. It's just knowing when to apply that maths. So 7.5 multiplied by 2, of course, is 15. So 15 equals, if that's 15 grams, equals our mass. And finally, we will write our answer. in words. So 15 grams of H2 are required to react with 2.5 moles of N2. So that was a mole to mass conversion. Very rarely comes up. Usually you're doing something like a mass to mass conversion, or sometimes like a mass to volume conversion. But remember, you always have to go through moles. So in this case, we're using moles at the end there because it asks for our answer in moles. But what about, and I've put up the full working here, what about if we start with mass, but I want to know the moles by the end? Well, first of all, I've got to convert my mass into moles. So I have 70 grams of N2. How many moles of H2 are required to make NH3? Remember, moles is the number of atoms. Like if I have 70 grams of N2, what number of atoms, and my units will be moles, am I going to need to completely react to make ammonia gas, or NH3? So we use the mass formula, mass of a molar mass. We find the molar mass of nitrogen is 28. That's nitrogen gas, because each nitrogen is 14. And so 14 plus 14 is 28. Technically, you can include that 0.01 in there, so it would be 28.02 when you get that answer there. But roughly, it's going to be the same. So we know that 70 grams of nitrogen is exactly 2.5 moles. And so when we go through that, I work out that 7.5 moles of H2 are required to react with 70 grams of nitrogen. You might like to pause the video to make sure you understand this concept. All right. I don't know why that's there, but we'll move on. Let's do a mass-to-mass conversion. This is, as I said, all roads lead through moles. So I have 70 grams of nitrogen. How many grams of H2 are required to make NH3? Well, first of all, we convert that grams of nitrogen into moles. And so we work out, and that's what came up there previously, it's 2.5 moles of nitrogen is 70 grams. So 70 grams, you have 70 grams of nitrogen gas that's in the air, that is exactly 2.5 moles. So 2.5 times 6.02 times 10 to the 23rd. That's a huge amount of atoms. Moving on. Now, of course, that doesn't necessarily mean I am going to make 2.5 moles of hydrogen gas. I've got to do my mole ratio. So we can see here, nitrogen to hydrogen is a 1:3. So that's going to have to be multiplied by 3 to get our full answer. Now you can just quickly multiply 2.5 by 3, or you can go through the whole ratio way of doing things. And I like doing this way because it's foolproof. You never make a mistake. And you will make mistakes on exams. Finally, once I've got that 7.5 moles, it's not my final answer. I know I need 7.5 moles, but how much does 7.5 moles weigh? Well, of course, I use the mass formula again, and I work out that 7.5 moles is... oh, that looks like a mistake there, doesn't it? Yeah, that is a mistake there. Always pays to proofread before you start the video, Mr. Collins. And as I said, let's say you make a silly mistake like that in the exam. You will get marked down, but not as much as you might think, because chemistry is actually not about getting the right answer so much as it is knowing how to get the right answer. So if you go through everything and you just muck up one calculation, it's possible you could still get an A+. For that question. More likely you'd get an A if you have everything else right, and it is a really tough 3-star or A standard question. But it's not impossible for you to still do well, because silly mistakes happen to everybody, just happen to me there. But the difference is you do have to check your work, like I did now, to make sure that you are getting the right answer. So let's do something completely from scratch, and I'll make the iPad screen bigger so you can see that. Let's do a completely new problem. I have 145 grams of hydrogen gas. How many grams of water, H2O, will I make if I have excess oxygen? Okay, well, here's how I would go about that. The first thing I would do, and this is the finale to the video, you'll be needing to do questions like this all the time, and it's important that you... I wanted to show you this so you could see how I fully work out a problem from scratch on paper. And I haven't actually done this one before, so we'll see how we go. Let's hope I don't make any silly mistakes. So H2 is 145 grams. O2 is excess, so don't even need to worry about it. And H2O equals question mark grams. And I want my answer in grams. Okay. So let's write out. So my first point of call was to write everything out and just summarize the question, making sure I've got all the information I need there, so I don't have to keep flicking between the answer paper and then my writing screen, or in this case, an exam paper. I like to summarize everything. It helps clear my mind and gather my thoughts. First thing, let's write a reaction. So H2 plus O2, we know, is going to give us H2O. Now clearly that's not balanced. Let's start with the oxygens. 2 there, and 2 there. Let's double check that. 4 and 4, 2 and 2, we're good to go. So that's the balanced reaction. So I can see I've got a mole ratio. I mean, there is a sneaky little 1 there, but I don't need to put that in because it's just 102. So it's a 2:1 ratio between the hydrogen and the oxygen, and as a 2:2, which is the same as 1:1 for hydrogen and water. Okay, so step 1 was to write out that's why I put that 1 there, that 1 here. Step 1 was to write out the equation. Okay, I'm going to now convert H2 into moles. So 145 grams, so step 2, 145 grams of H2 equals question mark mole. Let's get the mole formula out. Moles equals mass over molar mass. Moles is what I'm trying to work out. My mass is 145 grams. My molar mass, well, H2 is 1 hydrogen. Let's just double check that. 1 plus 1 is 2. 145 divided by 2. Okay, so if I have 145 grams of hydrogen gas, I have exactly 72.5 moles. So 72 times 6.02 times 10 to the 23rd number of hydrogen molecules. That's a crazy amount of molecules. Okay, so that's how many moles I have. Oh, let me just write moles there. That's how many moles I have. Let's hope the screen doesn't do any funnies on me as before. Next step, let's do our mole ratio. So I want to know how many grams of H2O will I make? Well, this you can really easily work out yourself. So H2 to H2O is 2:2, which is 1:1. Okay. The answer is 72.5 because it's 1:1, but let's go through the whole rigmarole of dividing things using the method that I taught you. So 1:1 is going to be equal to 72.5 is to x. So that means 1 divided by 1 is going to be equal to 72.5 is to x, cross multiply. X equals 72.5. Okay, great. Finally, step number 4 is to convert that mole, 72.5 moles of water into grams. So, question, 72.5 mole of H2O equals question mark grams. Let's do it. Moles equals mass over molar mass. Yep, good so far. Moles equals 72.5 divided mass is unknown. That's what we're trying to work out. Our molar mass of H2O. Well, let's go to our periodic table. We've got 2 hydrogens. So let's go back. 2 hydrogens, 1 hydrogen plus another hydrogen is 1 plus 1. Our oxygen here is 16, so it's 1 plus 1 plus 16. So that's clearly 18. And let's put that in the molar mass of water. Molar mass of water is 18. So that's algebraically 75 multiplied by 18 equals mass. 72.5 multiplied by 18 equals 1. And remember, molar mass is in grams, so your answer needs to be also in grams. So 1,305 grams equals mass. Okay, so that's 1.305 kilograms, but let's just write out our answer. I'll write it out in kilograms just for a bit of fun. So our question is, with 145 grams of H2, I can make 0.5 grams, brackets 1.305 kilograms of water, in brackets, in excess H2. I need to work on my writing, but I hope you've enjoyed and learned from this tutorial. I will link at the bottom of the video some more examples of the question that we just did, maths to mole worksheets, and I look forward to seeing you in class. If you have any further questions, please let me know, and I'm very happy to help you.